Good evening, good afternoon, and good morning, depending on where you are in the world. We'd like to present to you one article of interest. This is a high-tech article. I'd like to present it because it's in the public domain and also because it has some interesting knowledge that's up to date. Before I do that, I would like to let you know that this is for review, informational and educational purposes. It is not to take the credit for the intellectual property of the article. The full credit to the intellectual property of the article goes to the publisher, which in this case is Tech Explorer. Excuse me. And the story by Fabio Bergaman. And before I start the article, I would like to welcome all the people watching on Facebook Live. I do appreciate it. I hope you enjoyed the presentation. And let's get started with this. Now, as you can see here, our title headline reads, "A teeny component for record-breaking bandwidth. New modulator breaks the terahertz mark." And ahead of us, we have a picture of three diagrams. Actually, one picture with three diagrams in it. And for the first one, we have the detailed EC model with device material layers. And we can see the actual circuitry here, which is sophisticated. Then we have a simplified EC model. And we can see from coming into the resistance to El Paras all the way from one segment going down to ground. And then there's another part where it goes, one will go to C pad and the other one will go to 2C. So one C pad and then ground, and then the other one will go to 2C, and then it will go to where it's ending up at this last part of the node. And for the third diagram, what we have is on the X and Y axis, on the Y axis of course being the vertical axis, we have the formula of how this is calculated, going from 10 to the first as the base, going to 10 to the second. On the X and the horizontal axis, we have the plasmonic length, which is going from 10 to the first to 10 to the third. And as we see over from when we compare Y to X, we notice that as X increases, Y increases at the same, almost at the same rate, as we have technically three different rates here. We have one, which is in black, as we have it color coded here. Technically, technically we have four. Well, it only looks okay. So one is over the other trend. Okay. So we have 2D sim, 2D sim, 2D sim, and measured. For the first one, for the W slot in nanometers, the first one, as we see in black, actually has the highest trend, starting at 10 to the first and goes to 60. The second one, as we see here in the second graph, is 100 for the 2D sim. The third one is actually the line. It looks like some sort of like purplish line. And then there's another type of graphic that shows a range in the 2C slot. And that's also going up in the same trend as well. So we get the overall idea of what's happening. Now, plasmonic modulators are teeny components to convert electrical signals into optical signals in order to transport them through optical fibers. A modulator of this kind has managed to transmit data at a frequency of over a terahertz, which is over 1 trillion oscillations per second. And when we're talking about oscillations, we're talking about analog versus digital, because oscillations refers to digital, a digital signal. So the word signal, by the way, has two connotations. One has to do with the actual literal electrical signal, electrical pulse. Actually, I don't want to use the same word to define itself. And then also we have a wireless frequency pulse, and that's basically like you send something wirelessly. There's a frequency that determines the amount of electrons that's sent per second. Now, research from the group led by Jörg Leithold, professor of photonics and communications at ETH Zurich, have succeeded in doing just that. Previous modulators could only convert frequency up to 100 to 200 gigahertz. In other words, the frequencies that are 5 to 10 times lower, that is. Now, the work is published in the journal Optica. Modulators of this kind can be used wherever large volumes of data are transmitted as a bridge between the electrical world and data transmission using light. Data is always initially present in electrical form, and nowadays its transmission always involves optical fibers at some point. And what we see here is the actual demonstration of how this works, and the caption reads, "The modulator in gold transfers the information from an electrical wave to an optical one. Credit goes to Johannes Gruer as per Polarization Technologies." The next generation of mobile communications, which would be 6G, because right now we're using 5G, will operate in the terahertz range. Its backbone, the cables between base stations, lies on optical fiber technology. So just in case you're not familiar with what's called a base station, that's going to be basically your tower, okay? And that, because what happens with a telecom signal, you're sending to the tower directly from the device, and then it goes from tower to tower all the way to the base station, where its main, let's say, hub, if you will, is. And he said, "Our modulator allows radio signals and other electrical signals to be converted into optical signals directly and therefore efficiently," says Yannick Horst, who worked on the component during his doctoral thesis. For medicine and measurement technology, although the transfer of terahertz signals into, or that is onto, I would say into, but he says onto, optical fiber is already possible from a technical perspective. It is a laborious process and it currently requires several expensive components. The new modulators can convert the signals directly, reducing energy consumption and increasing measurement accuracy. Moreover, different components are currently needed for different frequency ranges. The new modulator can be used with any frequency from 10 megahertz to 1.4 terahertz. So keep in mind that there's 1,000 megahertz in a terahertz. There's a million, so a mega to a tera is, yes, 1,000 times. So we're going from 10 megahertz to 1.4 terahertz. Right. So we, as he said, excuse me, we cover the entire frequency range with a single component. It's therefore extremely versatile in terms of applications, says Horst. Other potential applications include optical fiber data transmission within and between high-performance computing centers. Last but not least, the components are also interest for high-performance measurement technology, including imaging techniques in medicine, spectroscopic methods for material analysis, baggage scanners at airports, or radar technology. Some devices of this kind already operate in the terahertz range today. The new modulator is a teeny nanostructure made up of various materials, including gold, and makes use of the interaction between light and free electrons within the gold. The technology was developed by ETH Zurich, and the device was manufactured by Polarization Technologies, an ETH spin-off that emerged from Leithold's group. At present, the company is working to bring terahertz modulator to market so it can be widely used in future applications in data transmission and measurement technologies. For more information, Yannick Horst et al. Ultra wideband megahertz to terahertz, that's MHZ to THZ, plasmonic EO modulator, Optica 2025, DOI 10.1364/ Optica, and Optica is in capital letters spelled OPTICA, .544016, provided by ETH Zurich. And the writer and the publisher would like to let you know that the story was originally published in Tech Explorer. Subscribe to their newsletter for the latest sci-tech news updates. So that will do it for the article. I just had one, and what I'm focusing on these days is quality over quantity. So even if I only get one article, but I think it's groundbreaking, I think that's more of a value than having multiple articles that are just so-so. And also, I'm trying to not include articles that are super technical. I know this is very technical itself, but I think the implications are quite interesting. So as people are more and more interested in telecom, I think this will apply. Before I complete the review, I would like to ask your opinion about the article. As relates to the article, entitled "A Teeny Component for Record-Breaking Bandwidth," excuse me, new modulator breaks the terahertz mark. What do you think of the article? Is it interesting? Is it relevant to your life? And does it provide enough information for you to get an overall understanding of what the article is talking about? You're welcome to give your opinion in the comments below, but I do ask that you keep it civil, as we're only trying to keep the conversation in a civil way, that is, only providing value and making the process better. So if you have any constructive criticism, and the key word is constructive, where you have solutions to things, but not in a sarcastic way, as in literally like, oh, I think it could be improved if we did X, Y, Z. That's more than fine to do that, but just make sure you keep it constructive and not deconstructive, as in just saying something derogatory just to be sarcastic is one thing, but if you have something productive, as in you have a suggestion to make it better, that's another thing. So that's what we're after, is constructive criticism. Also, we're looking for any other ideas about what articles the audience would like to see more of. Currently, I'm doing just sort of breaking news, current events, and science and technology. Alright, with that said, I would like to thank you for taking the time to watch this video in my review of this article. I do appreciate the viewership, and as we're trying to actually build the viewership and more people watching it, I do appreciate that. For all the people watching the recorded version, first on Facebook Live, and also people watching this live on Facebook, what I'd like you to do is I'd like you to please click the thumbs up on the video. That way more people can see it was of value, and more people would be able to watch it as well and benefit from current events and news that's in the public domain. Also, for all the people watching this recorded on YouTube, Rumble, Dailymotion, what I'd like you to do is please click the like on the video. That way it'll be pushed to the algorithm and more people would be able to view it and enjoy it. If you haven't already, please click the subscribe button. That way you'll have access to all the content on my channel, as I certainly do have a variety of content on these channels, which is similar content, of course, ranging from product to gaming review to course review, also AI generated content, such as storytelling, and also I'm going to be doing more things with AI news, etc. So stay tuned for that. So I'd like to wish you a great day wherever you are in the world. Take care, and I'll certainly talk to you next time.